Hello, we are Team 3, Oh-hyun Kwon, Hyunjong Kim, and Joon Choi, and I'm Hyunjong Kim. We're going to talk about single image super resolution that is widely studied in the field of computer vision. This is our table. Okay, introduction. Super resolution generally refers to restoring high resolution images from one or several low resolution images. It is divided into single image super resolution and multi-image super resolution depending on the number of low resolution images used as an input. However, since multi-image super resolution requires multiple images as an input, single image super resolution is more popular in terms of efficiency. This technique can generate an image with better quality, so it is very useful in various fields such as medical images and satellite images. There are conventional methods such as nearest neighbor interpolation, bilinear interpolation, and bicubic interpolation to solve this problem. But recently, deep convolutional neural networks called deep CNN have been widely used in single image super resolution and shows remarkable performances. Okay, we selected these three papers as our replication paper. Second order attention network for single image super resolution, image super resolution using very deep residual channel attention networks, and enhanced deep residual networks for single image super resolution. And we're gonna call these models as SAN, ARCAN, EDSR for short. And we decided to reproduce all of these three models, papers, to make a fair comparison with the performance. Okay, this is our learning setting that we use to replicate all the models, all the papers. We used grayscale images to reduce the required model capacity and to make learning simpler. And we trained 50 epochs with 16,000 iterations per epoch for all models and settings. And we trained with 3 losses respectively, L1 loss, MSE loss, and L1 loss with L1 with adversarial loss. And we didn't use learning rate scheduling, and we trained the models with patch-based method with patch size 96 by 96. Okay, first model, EDSR. EDSR is a simple single-scale super resolution network based on ResNet, as you can see in the figure. This model could handle single scale at a time, so we replicated only in scale 4. This paper proposed to remove normalization from the model, and it improves the performance greatly. We used pixel shuffle as an upsampling method and didn't use any residual scaling. And it's very simple and basic model, as you can see.
Second paper we choose is the RCAN or ARCAN, an abbreviation for Residual Channel Attention Network. RCAN architecture is consisted of several residual blocks, as you can see from the bottom line of the figure, and each residual blocks are consisted of several residual groups. Each residual group has convolutional layer, activation layer, and pooling layer. Also, similar to the EDSR, skip connections with additions are applied. Finally, the difference between EDSR and ARCAN is the channel attention. The channel attention is applied as skip connection in each channel attention block and multiplied to the output of convolution layer, making the attended output. Finally, after several residual groups, there is the upscaling layer to finally make the super resolution image output. Shortly, the ARCAN is an extension of EDSR.
This is the structure of main model SAN. SAN is a second-order attention network for more powerful feature expression and feature correlation learning. SAN mainly consists of four parts: shallow feature extraction, NLRG-based deep feature extraction, upscale module, and reconstruction part. They applied only one convolutional layer to extract the shallow feature from the LR input. NLRG also exploits the abundant structure cues in LR features and the self-similarities in HR nature scenes by RN and L modules plugged before and after SSRG. They used 20 sets of LSRAG module in shared source residual group structure for deep feature extraction. And such LSRAG module had 10 residual blocks with single SOCA module at the tail. SOCA is a second-order channel attention module for learning feature in interdependencies by considering second-order statistics of features. Therefore, SOCA mechanism allows to focus on more informative features and enhance discriminative learning ability. Moreover, this module has non-locally enhanced residual group NLRG structure to build a deep network, which further incorporate non-local operations to capture spatial contextual information and share source residual group structure to learn deep features. Besides, this model utilized shared source skip connection, which allow more abundant information from the LR input to be bypassed and ease the training of the deep network. Covariance normalization plays a vital role in SOCA, since it characterizes the correlations of channel-wise features. The first one is a simple covariance matrix which can be computed with I-hat and feature matrix or orthogonal matrix and diagonal matrix with eigenvalue in non-increasing order. And the next one is covariance normalization, which can be converted to the power of eigenvalues. In here, we changed I-hat size m by m into m by 1 to reduce the space complexity and computation as an improvement measure. To improve the main model SAN, we used another loss function, adversarial loss, and changed the space complexity. As I mentioned above, we could successfully reduce space complexity and computation of the main model by changing I-hat matrix size as m by m to m by 1. That is a sum of low-rank metrics. Before this, original model was impossible to fit because the memory usage had exceeded 11 gigabytes. However, by applying this method, memory usage can be reduced to 3 gigabytes, enabling efficient feed. We use div2k image set, and div2k has high-res images with corresponding low-res images and divided into train set and test set. We used grayscale image to lower the required complexity of the model.
From now on, I'm going to explain the results of our replication and advancement. These are the results of replication approach and improvement approach. The metrics PSNR and SSIM stands for peak signal to noise ratio. The metric PSNR stands for peak signal to noise ratio, which indicates the ratio between maximal signal and noise. And another metric, SSIM, is simply just a structural similarity, which is calculated using the mean and variance of each image. As you can see from this table, all the results have shown very similar metrics. Interestingly, however, the model RCAN had better results in mean square error loss and adversarial loss, but that tendency was not as stable as we had the learning curve in appendix. From now on, those are the resulted super resolution images. This is a comparison between different models, as you can see from this table. And these are the comparison between different losses in same model. Those are same in here and here, respectively, using different image, as you can see from here. To summary our presentation, we applied different laws and different models to improve those replication results. And there are some discussable parts. First, as you have seen in result table and result figures, GAN loss does not provide better results. Rather, the model using adversarial loss tends to produce more realistic super resolution images. However, those more realistic super resolution results might be different with ground truth. Secondly, the modified model, SAN2, had similar results while reducing complexity. We reduced the memory usage while learning by reducing the complexity as we have modified the metrics. To sum up, we have improved our model in complexity by reducing the memory size the model consumes. This is the end of our presentation, and thank you for listening.